Sorry. Today I'm going to talk about like two topics. One is factor analysis. Another is Fisher discriminant analysis. These two topics. And before that, because these two topics are related to PCA, so I just very quickly go through PCA first. And all these three algorithms depend on one theorem called principal axis theorem. And before I introduce these three, I just quickly go through the principal axis theorem. Let me write down the theorem here first. Say we have a matrix A, which is the symmetric positive diagonal matrix, and we have a vector Y. The ratio of Y transpose A, Y over Y transpose Y. The maximum value of this ratio is equal to lambda 1, which is the eigenvalue of this matrix A. The biggest eigenvalue, I mean. When you take Y equals to the first the eigenvector corresponding to this eigenvalue of A, this is the principal axis theorem. Let me prove that first. Well, if you take Y equals to the ith eigenvector of A, the value is going to be equal to the ith eigenvalue corresponding eigenvalue. This is principal axis theorem. Let me show that first. Well, let's start from a very simple case where we have a matrix lambda, a diagonal matrix lambda, and we have the Y, the same Y. The ratio of Y transpose lambda Y over Y transpose Y is equal to, this is quadratic form. This is the inner product of Y. So this is the scalar, this is the scalar. So the ratio here is equal to this term, this transpose times this transpose this, is equal to lambda 1 times y1 squared plus lambda 2 times y2 squared times lambda p yp squared. This is this quadratic form over inner product of y is y2 squared plus yp squared. And this is smaller than or equal to, okay, I should say this, lambda 1 greater or equal to lambda 2 and p. This, we can, if we replace this lambda 2, lambda p with lambda 1, we get y1 squared, yp squared, because this value are smaller than the corresponding term. So this is bigger than this guy, and we keep this unchanged. So we cancel these two terms. This is equal to lambda 1. So to summarize, if we have y transpose sigma y transpose y. This is equal to lambda 1 when you have only this term. So these two cancels out. We remove all these terms. So we only leave this first term. Then we have a lambda 1. This is the only case when they are equal. Otherwise, this value is smaller than lambda 1. So how do we remove all the rest terms? We only need to pick up 1 which is equal to this.
Is it always less than lambda 1?
Well, so as long as you don't take this value, they're always less than lambda 1. Because
just for that one,
yeah, because when you use this y, you actually only have this term. Actually, you can hit of course times the scalar, but just keep it very simple for all the rest of the y's. This is the case, and now here we are using a diagonal matrix lambda, but for this theorem we need a positive symmetric, positive diagonal matrix A. So let us try the case for A. So A, we can decompose the A into P, which is eigenvectors of A, and lambda and P transpose. This is the eigen decomposition because A is positive definite matrix. Where, let me see if I should erase this one. And where P is equal to these are each of these are eigenvectors of A. So these are vectors. And the lambda is lambda 1, lambda P. You can always sort the eigenvectors from the biggest to the smallest. So we have this guy. And so the ratio is y transpose P lambda P transpose y over y transpose. And if we look at this form, this is a diagonal matrix, like in this case, where we have a lambda diagonal. The difference is right now we have a different so-called y. So if we want to transform this problem into the problem we have already solved, we only need to define this term p t y is equal to z. And then this problem can be written as as we define this, and actually y here, because P is a matrix of eigenvectors, so we can P inverse is actually equals to P transpose. So here we can just times the P here times the P here, so we get y is equal to PZ. So we have these two formula. We can rewrite this ratio into Z transpose sigma, well, lambda z over y z p z. Y transpose is E transpose P transpose. And this term, because this is still a matrix of eigenvectors, so this is equal to I. And then we get a form Z transpose lambda Z over Z transpose C. This is exactly the same form as we proved before. So we have the conclusion that when Z is equal to 1, 0, 0, 0, we have a maximum value of this ratio which is equal to lambda 1, which is the biggest eigenvalue of this matrix A. And well, on the other hand, we have the Z defined as P transpose Y. So this is equal to P transpose Y. Then Y is simply equal to P times this one. This is equal to Y. So yeah, so here Z we let the Z to equal to this vector, and then we times P here times P here, so we get this. And because P is equal to E1, E2, yes, and EP, and when we times this to this, we have only E1 left. So which means if we want, well, which is basically this. Okay, that's roughly the principal axis theorem. But by the way, if you search for this principal axis theorem, you might get a lot of different search results. And somehow it has this thing.
Can you explain something why A must be symmetrical and positive angle?
Well, because here we assume the lambda 1 it's bigger than lambda 2. I think it's must bigger than or equal to 0. And this is actually the what do you call it? A property of symmetry, positive definite matrix, because you have to have all eigenvalues bigger than or equal to 0. Otherwise, this term can be a negative term. This is roughly not so.
You just want to make sure the eigenvalue is the positive
yes.
level.
Yes.
If it's minus, what's the problem?
What's that?
If y transpose AY is minus, what's the problem?
Let me see. First of all, because we are going to use the covariance matrix on this A, so often you don't even need to think about when you have a non-positive definite matrix what's going to happen, because we are going to use covariance matrix of the random vector, so it's always the case. But if it's not, I don't know.
You have a negative variance.
Yeah, maybe.
Yeah, you have a curve like.
Yeah, you have a like
that's curve.
So let me first quickly go through PCA. I think about 1 year ago, Sam has gone through this, so I just make it very short. PCA, well, in a lot of tasks, we actually care more about variance. For example, if you want to distinguish like two populations, you need their variance to be very high. If they are kind of condensed to a point, you can't classify them. So in PCA, the problem is we are trying to find a basis to represent the data better. So if we have like two-dimensional data x2, x1, it's like this. We want to, because they are highly correlated, we want to use only one axis to represent the data, which means we want kind of find the axis like this. And how do we formulate this problem? Well, the goal of PCA is to find the axis that when you map your data point to this axis, they have the largest variance. So to the contrast, if you find the axis like this, when you map all your data into this axis, you might have very low variance here. This versus this, obviously this is better. So first of all, given this point x, and say given a vector like A, how do you map this x to A? So what's the formula if you map this x into A, which we need to formulate this problem, because we have to map all each data onto this axis and then try to maximize variance. So here we need to find different A. You can call it A. You need to find different A to maximize the variance, which you have your original data mapped onto A. And the formula for this actually, this is perpendicular. For example, here, the point, well, every point on this vector you can represent as a coefficient times A, because you just like protract it or make it shorter. And this vector is perpendicular to this vector. So their inner product should be 0 because they're perpendicular. I mean, I know this is very simple, I just quickly go through it. And you have which is vector, this vector. This should be equal to 0. And if you times this two term, A transpose lambda, because lambda is the scalar, so it transpose is equal to it itself. So if we move, we are trying to find lambda. So we move this term there. We get lambda is equal to A transpose X A. And if we can further simplify this, if we assume this A is a unit vector, then if we put a constraint, then the lambda is simply equal to A transpose X, which is the inner product of this vector and the vector you are trying to map. So I just write this down here. So here we are trying to maximize the we are trying to maximize the variance of the mapped points. Right now I just call them lambda. And this is equal to actually the A transpose times lambda times A. This sigma is the covariance matrix of the original space. Before we transform it, it actually equals to this. And last time we talked about Gaussian distribution. We have the affine property of Gaussian distribution, which is this form.
Is R? A R?
Which one?
No,
Of this one?
No, the first one.
This one?
No, that's it.
Variance.
The variance.
Oh, okay. The big.
Oh, yes.
The variance big.
So what's lambda going to be?
What's that?
So the lambda.
Well, lambda you can consider that mapped A onto this vector.
The x onto A, right?
Yes. And is I can show this, but I don't know. Okay. It turns out if we want to maximize this variance, it's actually very easy. We can just increase A. We can make it arbitrarily large.
So the capital sigma is the variance of original data, right?
Yes, covariance matrix of the original data. Let me see if I should show it. Okay, so maybe I just show it.
Yeah.
It's better. Okay. Yeah.
Okay.
Yeah.
Okay. So the variance of lambda is an expectation of say the original data is A. Is these points here. And the variance of this guy is each x minus expectation of x. It's the same here. And
You want to put the transpose there? No,
what's that? Because
put the transpose.
well,
This is not scalar, right?
well here it is. Let me see. Well, the variance here. Well, okay, I really wrong. I was trying to remove the variance of lambda.
Alright, good. Why? It's just you need to put back the transpose there.
I mean, I want to write for each mapped lambda.
No, I guess that's okay. Isn't that just one step? Because you just put lambda there.
So
exactly
lambda minus expectation of lambda
Yeah.
because it's variance and lambda is scalar. So
Oh,
In your
I
case,
see.
lambda is scalar.
Yes.
They are higher dimension
Yeah.
than this one.
and each time we find one one vector, one basis for each time we find one. So each time we have one actually lambda in one dimension. So it's the same.
Yeah, it's fine actually. Actually, it should be one step.
Yeah, it's actually very easy.
Yeah. Yeah, I know. It's so where's the transport? This transport is this. If this is wrong, not the minus, not the, yeah, because the mean is, so, yeah, I don't know, it's messy. Yeah, so it's just,
Yeah, and in the middle it's a sigma. So it's there is sigma here. So yeah, so each time we are finding y-axis, so we just map into y-axis and try to maximize its variance. And because we can scale a to arbitrarily increase value arbitrarily, so here we still put the constraint of a transpose A equals to 1. So we want to maximize this variance is equal to maximize this guy. Okay, this is y anyway, it is constant, so we just maximize this term. So if we want to maximize this, according to that principal access theorem, we know when this is the max value is first eigenvalue when A is equal to E1. So which means we use E1 to the first eigen to map that at the first basis. And then this is our first basis, and the second basis. Well, you need to maximize the variance and try to make it independent of the first basis. Then you choose this, which turns out to be the second eigenvectors. And okay, this is, I think it's should be short enough. And right now we can either move on to product analysis and Fisher discriminant analysis. Fisher is shorter, so I just start with Fisher discriminant analysis. And let me make it a bit better. So say we have a points like this, and point like this. And in PCA, we didn't use any label information at all. We just consider all the input x and try to find a better basis to represent x. And often when we transform the basis, we often try to do some classification task. And but PCA doesn't consider that at all. In this case, we have such kind of data. It will try to find a basis like this to represent this data. And well, if unfortunately we are trying to discriminate these two groups, because PCA does not consider the label information, so it still tries to map these two groups onto this axis. So which means we will have something like this. And all information for discrimination is almost lost by this mapping. So instead of just trying to find a better representation, well, we need to first find a representation, but also it try to give you as much information as possible for your discrimination task. For the discriminant analysis, I think Shuang mentioned that last time. There are 3 types of algorithm for classification. One is the discriminant analysis. You find a function to separate these two groups, or you find the posterior distribution, or the well, or you try to use the generative model or discriminant model. For discriminant analyze, you try to find a function like this to separate these two groups. And if you look at this is moving your boundary, but this is actually this term. If you make this W unit vector, so it's actually you map this to you can consider it as map your original X onto a basis defined by W, and then somehow move the boundary decision boundary. In your case, if you imagine by eyeballing it, you might think, okay, we can find this function. And by definition, well, we find this hyperplane. By definition, this W is orthogonal to the hyperplane. And if you use this, if you consider this as projecting X onto the the norm or the vector which is perpendicular to the hyperplane, then you're actually mapping this point here and point here. So in Fisher discriminant analysis, you are trying to find a mapping W which separate these two classes as far further as possible, while keep each group as compact as possible. So there are actually two objectives you want to optimize. One is the difference between this group. You want to maximize the difference between groups. You want to minimize the difference within groups. So you need to find the mapping to do that two tasks at the same time. So how to measure the difference between groups, and we can if we find the mean of this group, and the variance of these means is describing how dispersed these means are. These means are center of the population, so it basically describes how further away your populations are separated. And within each group, you can use the same trick. You can compute the like variance to describe how dispersed the data within each group. So our goal is to find the mapping to, well, yeah, I just said it. So we can define the difference. We can define the two terms we just described. So we can sum. Let me see. So this J is the index for populations. For this case, we have two. We can have more. So for each group, the mu J is the mean of the original group. For example, it's here. This is mu I. Here is mu2. So y is mu2. And J is here is in the set of 1 and 2. So we have this mean in the original space, and we map that. Just follow the same notation. W. And this is the mapping of the mean in the original space onto this vector. And this mean and say the mean of these two means stays here, and we map it to here. And the mean of two means is like denoted as mu r, which is still in the original space, and square it. So it, well, if you just normalize it, or then you have the variance of the means. But here, because we are going to maximize the ratio also, the scalar here doesn't matter because it's just constant. This we can rewrite as, let me see. And because this value in the bracket is a scalar, it's a scalar here, so we can rewrite this as J. If we just write it, expand it, times this, and this is a scalar. So if I just take a transpose of this value, it should be the same value. So if I take transpose and this becomes here and this becomes here, so then I have this formula. And because this has something to do with J, it has nothing to do with W. So I just move W here, summation of this this term, and this. This is still in original high dimension. So this product gives you a matrix. Matrix, because if I write down like this, then it's a value. But if I write down like this, it's a vector. It's like this times this. It is going to give you a matrix. And here we define this term as B, which is between. This between describe the well, you can kind of call it covariance matrix of the original data, and this to W, like try to map this covariance matrix to here and find the variance in this single vector. Maybe it's a bit confusing. Let me see. It's like last time Sam just showed, if you have a variance of lambda, it is equal to A, which is this guy, times covariance. Here, the only difference is, right now the symbol is different, but this is all vectors. You map this values onto a vector, and this sigma here was the covariance of that. And here, instead we use a B, so it's the same. So this is, you can estimate this from your original data, but you need to somehow change this W to make it bigger. It's essentially the same problem with PCA. Probably it's a bit confusing.
Actually, it's going well. For me, it's okay.
Okay.
Actually, if you just write this your objective function and what you are trying to do, then probably you will clear to them.
Oh, okay.
Like what you are doing this way, and then like subjected to again like the transport one kind of like that.
Close to this. I can write it here. So we were saying we want to first maximize first maximize the variance.
Because you're doing the same projection, right? You're doing like W transpose mu J. You're saying like you want to see, okay, actually you can even plot that, right? You have cloud here, something like that. Then you have the center of gravity of those clouds, and you want to find the projection along the direction so that the sum of this projection, let's say if I take this projection here, the sum of this here will be kind of maximized, right?
Yes.
That's the movement.
And you
Or
want
like,
this.
or like I can try this direction also. And this direction may be not as good. Or I can probably make a bad example.
It's
See if I can-
triangle.
yeah.
It's
That's the
fine.
eraser. Yeah. Take the backbone and then something like that. And probably this is a good direction. Like I think this will be a pretty bad direction. So I have this here add together. So because you are looking for projection, again it will be that terms there because W transpose mu minus W transpose mu mean here will be like projection for I there. That will be the square will be the
Yes.
the square distance of this projection. And of course only when your W transpose W is equal to 1, right? So therefore I should have this constraint here.
Yes, and
And so therefore I'm just trying to maximize that way. That's what you
yeah,
want.
for this part it's almost exactly the same as PCA. And the second object we want to optimize is we want to shrink the mapping here as tight as possible. And
But you write the objective function is like that, right? You didn't have more stuff, it's just that.
In this case, you are considering the supervised learning case, right?
yes.
For the supervised, you should make sure the concept center as dense as possible. So for supervised learning, you have that, right? So you are going to talk to the supervised learning, right?
No, that's this.
Yeah, because here we calculate this. We were actually using the labels.
Yes.
Otherwise, we
Yeah.
cannot estimate the means of each group.
But I guess the formulation right here didn't have what you said, like trying to make it as dense as possible.
Yeah. That's it. I'm going to write.
Oh,
it.
you're going to add that after?
Yes.
Okay.
This term is just this term. But
So, okay. So,
and we need to have a. Oh, okay. This notation is bad. This is within each population. You want to make it as small as possible. So if you maximize this, minimize this, you have this whole term maximized.
But when you choose the ratio of them, not just
The summation.
like commander side.
Yeah, it's possible, but if you formulate this as the problem as this, you have that theorem. You can just use it. Otherwise, you can just have this term plus or minus this term times lambda, and you try to maximize this. And I think probably the similar procedure, but different maximization algorithms. And here we have defined this guy. And here within, well, this is very bad notation. This is better. And this is equal to. We are going to go through each of the group and sum the variance of each group and try to make the whole summation of variance within each group as small as possible. So I'm essentially doing something like this. So variance of the pi1 first group plus variance of pi2 first group, second group. Will map to this vector. I want to minimize this, the whole summation, or maximize this. Is it?
How can you get the variance without knowing the label?
Yes, in LD Fisher discriminant analysis, we are using the label. PCA, we don't use the label.
But the question is, you want to choose which point you want which label so that you can make the class as dense as possible.
Oh, okay.
So if you look at the direction.
This is training data. We know everything. We know X, we know Y. And for example, these are data of the weight of elephant. This is like weight of like mule. So we want to calculate the value.
No, I don't think it's this a difficult, simple problem.
So make it more complex.
No, I don't know.
Okay. So because we have this label, so this I can calculate the mean and the variance within this group. I can calculate the mean and variance of this elephant group. So in Fisher discriminant analysis, I'm using label. And even after calculating the mean, I want to calculate the variance of the means of different groups, the variances. So it's variance of mu, the average weight of mu, average weight of elephant, average weight of dog. This is describing how much the groups are separating. But within each group, I have a variance of x of mu. So because I have so many data here, I can calculate the variance. But after mapping, I want to make it very small. That within each group, it's very compact. But between each groups, I want it as further away as possible. This is like this. So, almost with the same logic, we can write the summation of square difference of within groups as almost the same form, which is just this. We want to right now. The problem is turned to maximize this term.
Okay. This was equal to this one?
Okay. I should, well, I don't know how to call it.
What was written on your notes, actually?
My notes has a bit more derivation, but it's too long, I think.
So what kind of notation do you use when you want to copy the notation to something else?
I saw two different materials. Each of them using different notation, so I mixed them together. Actually, this term was from Bishop's book. I think he used this, but he used S, B, and S, W. But this is from another book I read, so when I mix them together, it becomes confusing. Okay, if it's confusing, I just switch it to S, W.
What's the SW?
SW here is, I just erase it. So it's, you can think of it as a summation of variance of each group.
Actually, why don't you just write down the summation like what you did at the beginning? Like the summation IJ, then
Yeah, I tried to write it, but I saw them confused.
No, I guess they are more confused without that.
Okay, no, that's fine. Yeah, I can write it.
I think this is better.
Okay. Okay. Yeah, so by the same procedure, you get WT as by the same.
Yeah, I guess you write the step for
Okay,
that
here
step.
J is the label for the classes and I is the number, the
Within
population.
two.
Oh,
Yeah, so
yeah.
so J here is 1 and 2 for two different groups. I is
All of them.
well,
This is data within that.
yes, yes.
All
So,
of the
so this I is for J equals to 1. This I is for J equals to 2.
Two kind of eyes. Two kind of eyes for the J.
To what?
Two kind
To
of
get,
eyes.
yes. I think this I here need to.
Yeah, it's
There's
So
a
what a
description.
set there, like I in a set of J or something like that, like some
Just choose an
J
integer,
or
right?
something like that. Like, yeah.
Like this. Population, J's population.
Or like you call pi is a set that contains all the value up.
Yeah. This is better. And okay, right now we want to minimize this. Combine together, we want to actually maximize this term, which means we want to maximize this, minimize this. And again, we can try to use this principal access through. But looking at that, we know here we have nothing. Here there's a matrix. There's matrix. For using the same trick, actually, I can decompose SW. So where SW is equal to well, you can call it P transpose, which is for W. And this is the diagonal matrix, which means I can write it as transpose. And let's see. Then I'm going to define a variable for this guy, and then we have a y there.
And you wanna mix the W transpose, PW and big lambda W together as one.
And the
You mean
Y.
this too?
Yeah.
Yeah.
Multiple to W.
This
That's transpose.
that tree as a Y and that tree as a Y.
Yes.
Y transpose.
Yeah, this one is y transpose. This one is y.
With that one.
Multiple W transpose.
Yeah.
I mean, just
What?
I,
You can go ahead.
yeah, I guess I. What's the name? Like copy that.
P.
So I probably should excount that because I need to fit it. It doesn't matter. I guess it's better to have stats. Like the stats. So, I can write, this is actually what the transpose. What is it? So we have this. So this becomes the A. So as long as this is invertible, then it doesn't matter. So we'll try to find use that one. We'll find the minimum of this to satisfy the back condition for this A here. So after we find this, we can just inverse it back.
Yes.
You want to define this by transpose, right? Yes, then this is by transpose. This is y. This is y. So here we are trying to find the eigenvector and eigenvalues of this A, and then you just transform it back, and this is roughly the procedure.
But in another case, if you separate the ratio like a summation, then you can introduce a lambda control which part you want to have more width, right? And you just divide the summation by a unit vector only transformed by omega, then you get back to this formula, right? You can still solve this problem. But in the later case, you can control the width of the part.
So you have to like one weight on this, and
method is something like this. I'm not sure if it is really wrong. So since there's a unit vector, you can divide the term like this, right?
and
Then you try to maximize. This is a minus sign. If you maximum this, minimize this. You can still solve this. Or not. So here get on the line of B, and another on the line of I. Then you maximize this term. But in this case, you can control your lambda. You can decide which part has more width. You want your data more dense, or you want your center more separate, right?
yeah, I think this is
Is
true.
it? You do one.
I think so. And maximum.
So is there any output?
I didn't see this before.
Yeah, maybe some problem
If
here.
you think about the maximum of this, for example, that like the lambda equal to 0, and you will have this thing equal to constant. But there is nothing with the SW.
If you take W equals to 0,
Yeah, lambda.
lambda equal to 0.
The maximum happens. and-
Yes.
So
but
what's this now?
you're thinking
So
about
should
use
do this-
another way to optimize this.
Yeah,
Oh,
another
okay,
objection function.
That probably will be difficult to optimize. Yes. Because you are not sure you get the matching is actually positive definite.
But his basic assumption.
No, I mean you have B minus lambda Wi now. That doesn't need to be positive definitely.
We merge this two.
Yeah, you merge it that way, and then you try to maximize the omega that way. But this thing,
You mean?
you miss. This thing doesn't necessarily be positive definite, right?
So, even though B and W are positive.
Yeah, of course. Like for example, you take this
Oh
I,
yes,
this
yes,
I.
yes.
Oh, actually, I'm not sure. This is really that's it. If you have minus I, is that positive definite or not? No, of course not. Yeah, minus I is not positive definite.
Well, you guys see zero, right?
I mean, for example, no. I mean, for example, lambda is equal to 2, right? It's like minus I, right? Minus I multiply this will be like equal to minus 1. Right? That's
Yeah.
The eigenvalues are not positive.
yeah, you cannot.
Yes.
Oh, there's one point, final point actually. So, it turns out when you find A, you have such kind of property.
Excuse me, you done with the equation?
What's that?
Yeah, done with that equation. You just find A and T and Y. Yeah.
Yes, because
And
by
after that,
defining Y as this, we can rewrite this formula.
something like that. Yeah.
And then we find the eigenvalue of this A, which is this part down. This times this times this. But that eigenvalue is for maximize this term. Define that value of Y is to maximize the transformed term.
Yeah.
You want actually find W instead of the defined Y. So you need to multiply the transpose back to back to W. So you know, find the mapping here. So I think a consequence of this, the whole process is finally you get A. Finally you have a constraint of A times W within A is equal to 1 when, let's see, when I is equal to J, 0, I not equal to J, and this is the definition of W conjugate. So which means if you have say A1, and when you have A2W, they are perpendicular. So this is the definition of W conjugate. So you kind of map the original space onto some space like this. There was a paper.
Confused for the last. What do you say like for the last one? What's W11 there?
Well,
Conversion.
I think that kind of some conclusion like this. When
So
you
the A transpose is what you found from
From
the
the
Y
Y.
here, right?
oh, okay, so
This W or Y?
which one?
The A transpose. This is W.
Yes, W transpose. there are some matrix here.
What's I and J again?
Because here you are going to feature discriminant analysis, you are going to find a set of bases. So each basis is W conjugate. Well,
Oh, okay, you mean you prioritize the PCA where you start with the largest and then go down to the largest?
Yes. So in PCA, you find the bases are perpendicular, where there are eigenvalues or eigenvectors of the covariance matrix. They are perpendicular. But in this case, in Fisher discriminant analysis, these spaces are not perpendicular itself.
Okay.
But instead, they are W conjugate.
Okay, that's SW or what? SB? That's SW.
I think it's SWS.
SW is the lower one.
If my notes is not wrong, so it's no lower one.
So in here you are what?
Yeah, actually it makes sense because it's just you have the Y is going to be
Y is perpendicular.
that would be perpendicular.
Y is perpendicular.
Y is perpendicular.
Yeah,
Yes.
so you just multiply by W.
Yeah, you come back.
Well, multiply by that.
Come back to that. Yes. So
Here
by
Y
the way,
is the eigenvector. Right.
yes, in PCA we have E1, E2, E3. In Fisher discriminant
Actually, you
analysis, we
have
have
I
W1.
mean, you have this white here actually. You have this white here. You have this yi. After you get this is the eigenvector, right? What should I say? This y transpose y will be ij would be like delta ij something like that. And well, but this y transpose y is exactly equal to this one because this is w something like that. This y ij here is like I'm abusing notation, just like transpose b w 1/2 lambda 1/2. I mean, just here, because your y is defined like that. This is your y. This is your y transpose. Then this gets you back to S. So therefore, this is like delta.
I think I read two books and I hand derive it by myself. So I'm using different notations from different materials. By the way, the W conjugate or A conjugate, if you use the conjugate gradient, which is like gradient descent method, but leveraging the problem well, because when you have a quadratic form you want to minimize, you have the matrix given. So if you somehow can transform your direction of descent into the A conjugate form, then you are going to find the minimum value much faster than gradient descent.
So what do you mean the conjugate? So S is the conjugate of omega.
Let me say it again. So there is a set of vector. Let me call it W, W1, W2, Wn. And the vector is A conjugate. The definition of A conjugate is, say you have a W1 like here, but if you have a W2 like this, which is perpendicular to W1, then this is defined as these vectors are A conjugate.
But for all the vectors inside the omega,
Yeah.
if they are
If they are different, then they are A conjugate. more also. I know you guys still interested?
Yes.
Okay. This one is similar to PCA. And this is actually very, very simple idea. So it's called factor analysis. And from a generative model perspective, say we have an x observed variable, x1 to xn, which is in very high dimension.
Excuse me. For your previous equation, W transpose multiple SW W, what was the A, I and J? You said I equal to J is 1 and I not
You
equal.
mean what's I, what's A?
Yeah,
What's J?
IJ.
Oh, ij is the index of vectors, different vectors. I is a vector and j is a vector.
It has nothing to do with labels and like
Oh, okay.
It's just like to
Yeah, last time j is the
Yeah.
label of.
use KL.
Because I kind of write down different part at different time. So for me, it was not confused at all. Okay. So similar to PCA, factor analysis is just try to use a small number of variables to explain a small number of variables to explain a larger number of variables. So actually,
What's
in
xi?
graph,
What's xi?
xi is any like training sample.
And this x is equal to x1 and this xn. Now
Superscript indicate the I string sample. Subscript indicate the component of x, because x is like vector. So you have a lot of vectors here.
I should be
Upon the super.
up above x.
Your I should be the superscript.
I? Oh yes. And here, we just define. Actually, we just propose. We assume x is generated by this procedure, which mu is the mean of x. F is a well, because here x is like p varied. So f you can be m varied, which m is much smaller than p. I should give an example.
What are these symbols again? Was mu and LF?
Mu is the mean of the x.
So what is LF?
F is a small number of variables. Well, here x is the p varied. F is where m is smaller than p. So this is basically saying.
But you still have L, right? Make sure the answer of L multiplied by F is still P, right?
Yes. Which means these x are generated from p. This is just how you generate the x's.
So what is E there or F?
Here you can see some noise or something. This basically saying the x is actually in some subspace of the whole p dimension.
Your X is a single vector or is the whole training set?
Oh, x here is a single x here, p varied.
So it's I.
Yes, that's right.
So it's something like compression, right? You gave in the mean and F, which is much smaller than your original X, then you just send F to the receiver, and they can recover X with a high fidelity, something like that.
Yeah, even PCA, you can use that for compression.
Yes.
So that essentially is your X lies in some subspace of the whole P space. Otherwise, you cannot find the F to
So
represent.
what's the motivation you want to present it? Is for compression or classification?
You can use it to find some. For example, you have observed a lot of variables, but these variables might be caused only by a small number of reasons. So, but by this reason, these reasons cause a lot of things you can observe.
So you mean the reason here is X?
Yes, these factors.
But for different X, you have different F, right? So you have
Yes.
10X, then you have 10F. So you have 10 reasons.
You have 10X.
10F is, for example, the input data has 10. I mean, there are 10.
Dimensional?
No. I mean, number of data.
Number of data.
Equal to 10. Then you use this formula, then you get 10 number of F.
No,
Yes,
just
here.
reducing the dimension.
Here, this is variable. This is variable.
It's trying to solve the same problem as PCA, right?
Similar. Similar.
Because you can think of PCA also a dimension reduction.
Yeah.
Here is also dimension
Yes.
reduction.
Yes. So here, each F, because F is a variable, so each F corresponding to one X, because these are actually parameters. Given all these parameters, you plug in one F, you get one X. This is how you generate the data. And the dimension of F is smaller than dimension of X.
But the mu is based on your training data.
Yeah, all this we need to estimate from training data. In training, we estimate this variable, estimate this coefficients of parameters. But after getting all these parameters, you can generate F from X, or you observe X, you can do it inverse, probably find F by for example histogram.
I feel this is pretty old.
This is old. This is old.
Like in before 1910 or something.
Well, even
Not
maximum,
exactly.
even maximum molecular is old. It's 80 something.
Yeah, but I don't know.
Yeah, and a few steps we can just learn. Well, actually, then I can just make it short. I think the more important is to understand this formula rather than learning parameter. Well, the learning parameter one, we can still use the eigendecomposition. Another one we can use EM. Because if we want to learn the model, we use maximum likelihood. And using maximum likelihood, and there's a hidden variable here. So we cannot just use the maximum likelihood because the log is on the summation rather than the formula itself. So we use EM to estimate F and estimate parameter and then estimate F. One EM method. And this is a bit simpler. I don't know, if you think it's old, maybe it's not really worth spending time on it. But this is just like derivation, like last two algorithms. You just decompose you somehow find the covariance of X can be rewritten as L S transpose plus a term here. Here we can decompose that as a P transpose. And this term you can define L. And then you have this term, you can just subtract the covariance of this and this, and then you get this term. So this is pretty simple procedure. And maybe this is not used very often in the literatures. This is only for fun, actually, for practice. So,
can you give us a definition of factor analysis? You mean the eigenvector decomposition in the factor analysis? So,
the definition of what?
yeah, just what's the factor analysis? Just this formula, if you express your problem like in this formula, then you call this factor analysis.
Yes. This is, I think, in a lot of problem like Markov chain, I mean, they just define a procedure of how you generate your data. I mean, in terms of graphical model, for different configuration, you have different model. And this is just one model of explaining your data. Markov random field or hidden Markov model, there are just different ways of generating your observations. This is just another way.
So you use mean plus L multiplied by F plus L, then you are using the factor analysis method. So
yes, if your problem formulation can be written like this, yes, then this is a factor analysis required. And in graphical model, maybe it's easier.
Actually, I think it's exactly the same as PCA, right?
You can almost say that.
Actually, so it would be, if you pick the epsilon, it's like Gaussian noise or something like that, you just get a PCA. You subtract the mean and then you just, and then you try to find the F. Yeah, if you want to minimize the noise there, then you would just project to the one that is have the highest variance, right? And then you pick the P that has highest variance. The remaining noise will be minimized, right? So that the energy of the remaining noise will be exactly epsilon there. So the result will be exactly the same as PCA.
Even like PCA, if you choose this factor as the P variant, then you don't even have to you don't even use this error term. You can represent your X with the F exactly. If you choose to use P variant instead of M, which is less than P. So this the information loss of choosing a smaller number of factors is the reason of you have this error term. Just like PCA, if you keep all your axes, all your bases, you actually keep all your original information. You just change your basis. But if you cut some of these bases, then you are throwing some axes away and by reducing the dimensions. But if you keep all these axes, well, exactly the same information is kept during the transformation. Here is exactly the same case. And if you follow this way, you can almost say this is that PCA. But here, solution, the way of solving the problem is different. But the meaning is similar.
No, I guess only when your noise statistics is different, it will be, if you just pick a Gaussian noise, the optimum will be just do the algorithm decomposition, just get the PCA. That thing should give you optimum solution. It looks like, if you assume the Gaussian noise is symmetric, like basically in all dimensions it's the same, like an epsilon.
Then
can you show us?
I mean, okay, it's just, okay, if I try to do this, then it's minus mu, right? Just go back to it's minus mu and go to this. Then I try to minimize this noise here, right? Okay, I should say, okay, I said something wrong actually. I should, it doesn't even relate to the noise statistics. So if I have this, and then I want to try to minimize this, right? How to minimize that? I would try to, this L here, I will project to, okay, there's something like, I should pick this L to be making sense So in a sense, this should be a unitary transform, something like that.
What transform?
Unitary, I mean, it's just rotation.
Okay.
If you change the name, it won't be fair. Right? So
if you rotate f, how do you get the higher dimension x?
no, I mean no. I mean, think of this as x minus mu is equal to. Okay, let's just put the eigenvectors there. So I diagonalize this, then I have some eigenvector there, and let's call this y there. So, well, I should write that. I think I should write this is equal to some of py there. That P is the rotation matrix that I am going to okay, I need to be careful with notations. So let's say I have n of this first x1, x here, and so I have the mean there. So let's start with graphical model. Okay, we will start with the graph first. So what I'm saying is that let's say you have something here is the data, right? So what this formalism is just saying that okay, if you shift the mean there, you want to find the f there, like it's like lower smaller dimension. Let's say the dimension is just 1D. This is from a 3D. Like reduced to 1D there. So after this transform, you get back this data. So L can be something like, let's say, I'll pick the L is just along this axis here. So what do I mean is like basically I have this vector, maybe I call it P here, and then I will have basically each of these points now will be something like let's say this is x1 here. This will be after the projection, let's say this y here. So this is a new vector. So py1 is basically equal to this. Let's say this is the mean here. It's equal to x1 minus mu here. Something like that. So then I want this noise to be small, right? So the noise to be small is just saying that I want to make sure that this difference here, okay, actually this, I should write this should be approximately equal to this because this is just a projection. This would be something as epsilon there, right? So epsilon is equal to x1 mu minus p1 there. So what's that? This thing, this error here, if I look at the long there, it's just this way. So I want to minimize this epsilon. It's just doing this exactly the same thing as PCA. I mean, I'm just trying to, okay, what I'm supposed to do is, after I look at this x minus mu here, if I centralize there, then I should, basically it's just, I have p dimension. If I start with p equal to 1, then I should just pick the first dimension that takes the most information, right? So if I take this projection, then the remaining error will be like projected on the what's that called? Residual space, no, dual space of that axis, right? So then if my P is 2, I will just pick the second one, right? The second one is largest. For example, if I have P equal to 2, if I have a solution like, okay, actually this is okay. Okay, I start with 3D and now I'm confused myself. So if I have this and then I pick a P equal to 2, maybe it's like something with some dimension like that. And let's say you have this actually flat, let's say there's another dimension there. Then your remaining error will be something like this way. If I have a point here, then my remaining error will be something like that. So therefore, like, you just get PCA.
Sure.
And that's how you define. I mean, of course, then you need to claim.
P is what?
P is just L here. So for example, I have P for one dimension. My P is equal to, I have a P1, I should say. And then if I have a 2 dimension, I have a second axis like P2 there. Let's say this is P2 there. Then my L will be something like P1 and P2 there. So actually, that's it's better for me to put a transport there. But that's the transport. Actually, I should do transpose there. Actually, I should like this. So your first dimension will get, for example, if I have this say y1, right? If I only use one dimension with the y1 here, of course I should be multiplied by LF. This is L here, LF here. So this is F here. So let's say if I have 2 dimensions with it like that. So the first dimension I pick up this, and this direction is P1, and this will be Y1 here, something like this will be Y1 here. Let's say if I have this is the X1 here, or like let's say X1 is here. And then like let's say this is mean here, then my P2, let's say this direction here is P2 type here. Then my Y2 is like that, Y2 here.
So how do you get P? How do you get P?
P is basically just the eigenvector. If I use exactly PCA to do that.
Yes, because well, if you
I know you don't have a constraint here. You're saying, but L cannot be arbitrary, right?
right. So
Yeah.
so I mean.
Of course,
So-
there's lots of. I mean, there's lots of options
Yeah,
for you
because-
to pick
because-
L.
Because
I know,
L.
but there's no point, right? If you pick L, I can always put something like this multiplied by AA transpose, something like AA inverse, right? It doesn't do anything. I can always put any matrix here to make another L, and then I put another F there. But what's important is that I want to minimize this epsilon and this dimension as more as possible, right? Of course, PCA won't give you all the solution, but that's the intuitive and make sense solution. Right? I don't need more solution. I only need one. If I want to generalize more L, I can just multiply A there or something like that.
So you mean in PCA they gave you all solution, and in this case you only get one solution? Like
Oh, actually, no,
you
the
gave
other way. I think PCA gives you one solution. Because PCA you pick eigenvector, right? But what I'm saying here, you didn't. I don't know because I'm not familiar like the original one. Here, if you don't put any constraint on L, it's kind of silly. I will pick L to be like each column to at least to be a univector. Otherwise, it's
Yeah, I think because if you choose L
I
as
want to put, yeah.
if
You can pick anything, it doesn't make
yes,
any
because
sense.
if you choose L as any like column vectors, and if you combine the column vectors by any coefficient like f1, f2, f3, you can always, well, this is p by 1, each of them. You can always get p invariant variables by choosing any L and F. But some of these spaces are not good enough so that your error term is very big, right?
Yeah, but that's what I'm saying. If you use PCA, you will get the smallest one anyway. But if you want to add another L, I mean, PCA you will give a formulation, give you whatever, I forgot what, let's say I call this, use the same notation, let's say I call it L hat there, L tutor there. But what I'm saying that I don't care, I have this epsilon should be minimum anyway. Of course I can pick another thing multiplied in transpose, so I have another F and I have another L, but I don't care, what's the point for that?
The error is the same.
Yeah, it's all the same. So as long as I find one solution, I know PCA will give me that solution as well.
And actually, when they talk about this, they usually combine this with PCA, so they don't say they are different.
Yeah, actually some people just say they are the same.
Yeah, I think here we just...
This is all historical thing, I'm not historians.
I guess here we just go through different derivation and see different problem formulation. It's not like some like rocket science, but still, I mean, by solving this with different ways, you probably get a better understanding of existing algorithms. I think that's the point of this. Are there any things to discuss? You guys sleeping?